So my name is Alois, and I will joint work with Floyd, which is there, and my supervisor Jörg. And the title of the paper is Fuzzy Presheaves are Quasitoposes. So let me try something for this presentation. I will, since it's a theory presentation, I will try to give you the meat of what this paper is about, so that you know like what to retain from it, and maybe know like what to look for in the presentation, that the part that interests you. So the contribution of the paper is summarized as like we prove that the class of categories, namely fuzzy presheaves, which is a notion that we introduced, are all RM additive quasitoposes. And why is that useful to know that you are an RM additive quasitopose? It's for many reasons. For instance, there is a PDPO plus termination technique with Floyd that he will present in exactly 2 hours here that needs the category to be an RM additive quasitopose. Also, the formalisms the people have that he defined subsumes order when you are in a setting of a quasitopose. And also, quasitoposes have been proposed as a natural setting for nonlinear writing. And now, why do we care about fuzzy presheaves? Because fuzzy presheaves offer a practical treatment of graph relabeling, and I will illustrate that in a slide later. So this is the takeaway from the presentation, if you want. So in the title, there's fuzzy presheaves, as I will define it later. First, presheaf, just a quick recall, and if not everybody might know what it is. So a presheaf on the category I is a functor from I up to set. So what that means is that for every object in I up, you have a set, and every arrow in I up, which I call like heading of iota, you have a function. And the identities of composition must be preserved. And a presheaf morphism is simply a natural transformation between the functors. So a function for every object in I, every object I in I up, and a natural T-squared musculus. And this gives you a category called the category of frictions. And why is that useful? I really like this definition of presheaf because it's visual. And the category I up gives you a template of what the presheaf will give. So if you take the category I up to be just one object, presheaf is a set, and presheaf morphism is just a function. So you retrieve the category of sets. Now, if you take 2 objects in the category I up, you have a presheaf with just 2 sets, you obtain the category set squared or set times set. If you add an arrow iota between them, you obtain the arrow category. Now, if you add another arrow, I mean, this is probably the example that all of you know. If you have 2, you have a presheaf is like an edge set, a vertex set, and a source and target function. So you retrieve the category of graphs. What's interesting is we can extend on that famous example of how we can see graph as a presheaf. Like we can add like a 3rd arrow, where this time like an edge, there's still edge set and vertex set, but this time an edge has like 3 components, like a first source, a second source, and a third source. So the category that you obtain is the 3 uniform hypergraphs. You could add as many arrows as you want, and you can have hyper edges of the size that you want, giving k uniform hypergraphs. And you can combine the last 2 examples to obtain like where you have like 1 set for every integers that you want starting from 2. You could also start from 1 if you want hyper edges of size 1. And this gives you hyper edge of every size that you want, so the category of just hypergraphs. And with this notion of hypergraphs, note that the homomorphisms preserves sizes of hyperedge. Whereas there is another possibility for hypergraphs where you can define it on the walking, if I up is the walking span, then you obtain another notion of hypergraphs where you allow multiple instances and where the notion of homomorphisms don't require sizes of hyperedge to be preserved. And until now, like we've seen like ordered edges. If you want to have undirected, if you want undirected, you can do that by changing the category up. So you can define composition, and if you add like a symmetry arrow here, with those equations, you obtain indirect graphs. And another possibility is if you add like a reflexive arrow here in I up, you obtain what is like called reflexive graphs or degenerative graphs sometimes. So that's the reason why I can really like presheaves, is because by defining a graph, like a category where you have composition identities, you can obtain many categories of graphs in one go. And the beauty of that is also in that result that every presheaf category is a topos, and topos is a very strong construction because topos also quasitoposes, also additive, etc. So being a topos is neat, and you have all that in one go. So this is like the setup where we've seen like with the beauty of Presheaves. Now let's talk about the second part of the title, like of fuzzy Presheaves, like fuzziness. Fuzziness, I guess just a quick recall. What is a fuzzy set? It's a set where it's no longer, membership is no longer binary. It's no longer in the set or out of the set. So you have a range of membership from 0% to 100%, right? And the corresponding notion of morphism for fuzzy sets is just a function that does not decrease membership. And visually, a set is represented as a Venn diagram, and a fuzzy set you just blur the border, right? That's hence the name fuzzy. While the closer you are to the center, the bigger the membership, and to the outside, the less the membership. You take as a convention that you have membership 0, you are not in the fuzzy set. And if you want to have more general definition than just having the unit interval as your range of membership, you can take any poset of your liking. But for the presentation, for the slides, I will usually have like membership in the unit interval and written like in superscript, like this, for easy reading. So this is the notion of fuzzy set. You can easily have also a notion of fuzzy graph where you just have membership values on both vertices and edges. And the notion of morphism just asks for both functions, but for graph morphism, do not decrease membership, generalizing the notion of fuzzy sets. So for instance, if this is a graph, just put a membership on anything, and this is a fuzzy graph. And for some authors, what I've done here is like illegal. Like here I have an edge with membership 80%, and it has the source with membership 50%. For some authors, there is this requirement that the membership of an edge must be smaller than the membership of its source and of its target, which makes sense if you talk about membership, because for instance, if an edge is fully in the graph with membership 100%, it makes sense that the source and target must be 100% in the graph. So why do we care about fuzzy structure? It's interesting because if you see the membership as a label, so forget that it's a membership, just take it as a label. But now the labeling set has a structure, poset structure. And when you ask for that poset structure to be a lattice, a complete lattice, so you have join, meet, bottom, top, then the formalism TBPO plus gives a practical treatment of graph labeling, where, for instance, if you have an edge and the source has like label X, or membership X, but now we see it as a label. If you want to change it from X to Y, you can do that in just a single TBPO plus rule. Whereas, for instance, if you wanted to change the membership on the edge, this is something that you could do in TPO, for instance, but then it would not really be called relabeling, it would more be called replacement, because you could delete the edge and create a new one with the label anyway. But doing that, where you change the label, whatever the context, and without touching the context, this is not possible in DPO, but it's possible in TBPO plus, thanks to this feature of having join, meet, bottom. So this is the motivation. And generalizing fuzzy set and fuzzy graph, we define the notion of fuzzy Presheaves. So if you take a category I and a functor that gives a poset for every I, every object in I, fuzzy Presheave is a Presheave endowed with the lax natural transformation. What does it mean in practice? It means that for every I, you have like this membership set of labeling set Li, and for every I, you also have like the membership function. So on every level of the I, we have a membership function or labeling function. And what it means to be lax? It means that this naturality square, instead of commuting, it must commute up to 2 morphism in poset, which just means like less or equal commute. So if this is a function, it must be smaller than this one. And the notion of morphism is as before, like on every level, it must not decrease. So in practice, what it means that if you take I up to just be I, before we had set, now you have fuzzy sets. If you take this one, before we had graphs, now we have fuzzy graph. If we take both sets like LE and LV to be equal, and if we take this poset morphism L iota to be the identity. So in fact, this definition of fuzzy Presheave is more general because you can put the constraint that you want between the levels. So if you want to obtain the notion of fuzzy graph as before, you just take the identity here. But you could ask any other constraint. Like you could add the constraint that the membership of the edge is smaller by a factor of a function that you want, for instance, of the source packet. So you could do more stuff if you want. And you could keep going. Like if you take that before you had 3 uniform hypergraphs, now you have fuzzy 3 uniform hypergraphs, and you can keep going. And what is known about fuzzy sets is that when L is a complete Heiting algebra, then, which is the case, for instance, for any Boolean algebra or for the unit interval 0, 1, but you have a quasitopos. And what we extended to is that now when you have like every level being a complete Heiting algebra, is still hold, like we still have a quasitopos, but also that we have our additivity. So now the rest of the slides will be like giving a high level idea of the proof of like what's the interesting concepts behind those proofs are for those that are interested. And yeah, we start first by the quasitopos part. So to be a quasitopos means that you need like a few things to be satisfied. You need finite limits, finite colimits. You need regular subobject classifier and no Pellicati clause. So I will try to give like a idea of what those concepts means for those of you that don't know. First, I will just prove 2 limits, like give the idea of 2 limits, and start with the terminal object. So it's an object that has a unique, that every other object has a unique arrow into it. And for sets, it's a singleton set. For graph, it's 1 vertex and 1 loop. For Presheaves, you just generalize both cases as such. And for fuzzy set, you take the terminal object of set and you give full membership to its element. Similarly, for fuzzy graph, you take the one from graph and you give like full membership to every element. So with no surprise, this is the terminal object for fuzzy Presheaves. You take the one from Presheaves and you give full membership to every object. Similarly, the product, which is like an object written from 2 and has 2 prediction and a universal property. In set, it's the Cartesian product. In graph, it's called the tensor product, with the definition as such, like in the details of it. Or visually, you could like this is the image that you find on Wikipedia if you look. The product of those 2 graphs is this one. And generalizing to both of them, you have the product for all Presheaves. Now, if you look at fuzzy sets, the way to define the product between 2 fuzzy sets is the product in sets. And you just have to take like a function, specify the function and on the product, which is just the meat of the memberships. So similarly as for the terminal object, the way to have product for fuzzy Presheaves is just to combine the examples above, and voila, you have it. This is the idea for like the limits and colimits. The rest of the limits and colimits are similar. And as you can see, just combine what you already know, and it works. Another thing that you need to be a quasitopos is to have subobject classifier. So informally, the definition is like there is a pullback where, but visually it's like this: that you have a bijection between subobject and characteristic function. And I really like this definition because I feel like it's quite needed, quite visual, also in the graph example. But for sets, we all know that there is a bijection between like subset of a main set B, and every subset A corresponds to a function from B to the set 0, 1, where if you are like in the subset, you are set to 1 and with 0 otherwise. And now, if you ask the question, can you also do this thing in graphs? Yes, you can. And if you take, for instance, that graph B and this subgraph A, this is in correspondence, one-on-one correspondence with characteristic function from B to this graph omega. And we like this graph omega because visually it tells you everything that can be, that the subgraph can be. So for vertices, there is 2 options, 0 and 1, where 0 means the vertex. If you are sent to 0, it means the vertex is not in the subgraph. And if you are sent to 1, it means you are in the subgraph. And then for edges, there is like multiple cases, right? If your source and target are not in the subgraph, you cannot be in the subgraph. If your source is in the subgraph, but the target not, you are set to S, vice versa to T for the target. And now if an edge has a source and target in the subgraph, there is 2 options. Either the edge itself is in the subgraph, which is 1, or the edge itself is not, set to ST. So really like it. And you can generalize both examples and obtain a classifier for all Presheaves. Now, if you go to fuzzy sets, there is no omega that classifies all fuzzy subsets. This is because of the nature of fuzzy subsets. But what you can do, the most that you can do is to classify all regular fuzzy subsets. Where regular fuzzy subset means such that if you take, for instance, just an example to illustrate, if you take the fuzzy set with A membership 40% and B 60%, and A as a subset with membership X, it's regular if and only if X is equal to 40%. So you need to be called a regular fuzzy subset, you need to have the same membership as the main fuzzy set. And if you take omega to be this, so the classifier for sets, and you give a full membership to everything, you obtain a regular subject classifier for fuzzy sets. So again, this is like a list of 4 examples, and you just combine them, and you obtain with the idea, you combine the IDs. And if you take the classifier for Presheaves and just give full membership to everything, you obtain a regular subject classifier for fuzzy Presheaves. And last thing to have is locally Cartesian closedness. And again, I'll just give a partial part of the definition, but not of this one. So to be first, like a smaller version of the definition is to be just Cartesian closed, which means that you have exponential objects for every A and B. You have like B to the A, and you need to have like currying, or in categorical terms, an adjunction between functions of this form and functions of this form. And again, if you look, you can do that in sets, it's the set of all functions. You can do that in graphs with those definitions. You can do that for Presheaves. You can do that for fuzzy sets with this like nice equation that tells you what happens on the membership. So combining those examples, you can find exponential objects in fuzzy Presheaves. And now this is the proof that it's Cartesian closed. Now, how do you prove that it's locally Cartesian closed? Locally Cartesian closed means you don't have only exponential objects, but you have exponential objects on all slacks categories. And I don't know if you remember it, but this the proof for Presheaves is very neat. It uses the fact that Cartesian closeness is a property that is stable under equivalence, and that if you do slice a Presheave, you just obtain another Presheave. So since you know that the other Presheave is Cartesian closed, you've proved that the slice is Cartesian closed. For that, you just need to change the category of the Presheave from I to an element category, the category of elements, if you know what that means. And so this is like well known, since in that textbook. And what we did was like generalize it to now fuzzy Presheave, where you just need to again change the I for the category of elements, but also change the functor slightly, and you still have an equivalence. So this proves that you have locally Cartesian closed. This is the idea for Quasitoposes. Now I will give quickly the idea of how we prove RM additivity. I won't recall the definition, but it's most of you probably know it, but it's like having some square property, which is the most Venn-Kampen, all stable for the last one. So there's those 3 notions of additivity, like 2 beginning from the first definition. And this is like the status of what you have in general. So every topos is additive and every Quasitoposes is RM quasi-additive, so the 3rd version. And what we wanted was to obtain this middle criterion. So for that, there is thankfully a nice criterion in the literature from Johnstone that tells you when you are in a Quasitopose, you just need to have like closed, some property on unions, and if it's satisfied, you are RM additive. So this is the property that we used to prove it. So that's it for the proof of the main theorem of the paper. Of course, when we did that, then there was like one last question that we asked ourselves. So we've proved that all fuzzy Presheaves are RM additive Quasitoposes. But if you've been careful in the examples that I gave, there was one that was missing, one big one, which was simple graphs. Simple graph is not a Presheave, so it's not containing the results that we have. So what to do with simple graphs? Thankfully, in the literature, we know that simple graph is still a Quasitopose, both directed and undirected. And so we extended on that to obtain the same for fuzzy simple graphs. How such? The proof for simple graph is the notion of topology on topos and of separated elements, with this result from Johnstone that if you are in topos and you take all the separated element for the topology, this gives you a subcategory, and that subcategory is a Quasitopose. So this is a nice property that exists in literature, and for graphs, it's really stunning that if you like, this allows you to go from graphs to simple graphs. So I will give like a sketch of the idea behind it, but the details will take too much space. But roughly, there is one special topology which is really cool, which is the double negation topology that does the following: where if you have a subgraph, so like the same example as before for the severity classifier, but if you have a subgraph and you do the double negation of it, you just add all possible edges that you could have been missing. So for that, get like that red edge, the source and target were in the subgraph, so now the double negation adds it. And because of that behavior of the double negation, when you start with graphs and you go to the separated element, you obtain simple graphs, and we extend that where we started from fuzzy graphs, and if you take the separated element, you obtain simple fuzzy graphs. There is a slight subtlety where graph is a topos and fuzzy graph is a quasitopos, so we just needed to change a bit like the notion of topology behind it, but the result still worked. So this is a summary of what we did. In the same way that Presheaves generalize a lot of categories, fuzzy Presheaves that we introduced generalize a lot of stuff. We prove that all of them are RMLs of quasitoposes given that we have complete hiding algebras. We prove also that simple fuzzy graph form a quasitopos. And for future work, we could dream of proving more categories to be quasitoposes, because this is like something that is quite difficult to know. Like if you have a category at end and you like it and you want to know the properties, proving that it's quasitopos is sometimes very difficult. And having general like theorems or general tools to do that is always nice and handy. For that, now we just prove for fuzzy Presheaves, but we could ask like, what about fuzzy categories? Sadly, there is no consensus of what the fuzzy category is. Like if you look in the literature, there's multiple attempts to defining it, but it's no consensus. So if one day there's a consensus, we could dream of proving that fuzzy quasitoposes are also quasitoposes. Or another line of work that I've been following since this article is to try to study more this last thing about topologies to obtain more quasitoposes to see like if there's stuff to be discovered. That's it for my presentation, and thank you for your attention. So any time. Yeah.
So example, for fuzzy graphs, where you have the I as identity, so you can, for example, like you have the end of that one, yeah. So what happens if it's not the identity? So what kind of fuzzy graph you get in that case? It's not graph at all.
You obtain a different notion of fuzzy graph where the constraint between the membership of the edge and the membership of the source target is as what you want. You just need to have like here a poset morphism. L of iota must be a poset morphism. And for that, and a poset morphism is just a monotone function. So if you take the identity, it works, but you could also have something like a projection that raised the membership up to whatever value you want, for instance.
You could say membership of the nodes need to be twice the membership of the edges, something like that.
Yes, if you have like a setting where like taking the double is a monotone function. So from 0 to 1, you would have like maybe take the double until like half, and for half everything to 1. So for instance, if I'm not mistaken, in that's indeed a monotone function, you can need like just add like factor 2 in front of the condition for the edge and some target function membership. Yeah. And if you want to don't want that relationship, that constraint between the memberships of label and edges, you can also remove that part of the definition and the results still hold. Or another way to do it is, for instance, to send everything to top, because having like everything to bottom, I guess, because the bottom is smaller than anything. But you could also just remove that constraint and the results still hold if you don't want that. And at first, we didn't want to have that constraint because for the reason that we want, which is like a relabeling, this is not needed, because having this constraint just reduce the number of what you can call a fuzzy graph. So it doesn't change the application that we're actually doing. Just restrict if you're like him. Yeah, other questions?
Yes. So you mentioned very briefly that apparently these fuzzy sets are quite well known, and then for fuzzy graphs, it seems any other applications for these fuzzy graphs you have in mind? Or I mean, you see they have a very particular listening application, but did you in your research find any uses for these fuzzy graphs maybe outside of mathematics?
So yeah, except seeing, so I don't know the normal use of fuzzy graph with the membership. I just know the one where you see the membership as like any label that you want. I guess like maybe like yeah, fuzzy set is like fuzziness is used sometimes like in AI or neural networks. So I guess maybe the notion of the like neural networks where they have like strength of connection is represented by membership. Maybe it's some kind of fuzzy graph that they use.
Well, I mean, that was my question because it seems like now technically one of the obvious applications seems to be that graph transformation using the particle structure with ability to change weights and neural networks.
Yeah, exactly.
It's will have like I don't know if that's useful, but I mean you could introduce new actions, computing effectively some sort of. I mean, that's fine. No, you do now these push outs and pullbacks, and then particles with the weights and controls model for edges and have weights right. Oh, it's you can do the writing. That's the sort of relationships.
So I don't know how they do it in AI or how they change the weight, but they do it automatically. So I'm sure there is some technology behind.
The application of fuzzy graphs in machine learning. I mean, that's networks. I mean, essentially, there should be relations to neural network, but I'm not sure that actually sort of physically work with fuzzy graphs.
Yeah.
As a notion. But there are other forms of machine learning, I think, that were based on fuzzy graphs.
Mm-hmm. Yeah, I have a friend in engineering that told me that it's used, but yeah, I have yet to discover and study how. That's a good question, and that's a good application potential.
And you could do all the hypergraphs as well.
Yeah, you could do hypergraphs. Yep. Yeah. So this is included in all Presheaves. Yeah, which is neat.
And then the other question was, so which role is the hygiene algorithm play? I mean, is that a strong restriction? Patients of you. I remember reading this book about negation instead of double negation. So exactly workaround here, not having the hygiene.
Yeah, good question. So for the fuzzy sets, if you have a complete hygiene algebra, you have Quasitoposes. It's kind of natural requirement to us because a complete hygiene algebra is like by definition. Like if you see a poset as a category, to be a Quasitopose is the same as to be a hygiene algebra. So it corresponds to it. Now, for this theorem here about Stout, like this is like an implication, but is this an if and only if? This is not known yet. I tried to look into it if it's an if and only if. It's not that obvious. It looks like it also should almost be the case. But for instance, already like if you take bottom, the top element is guaranteed by the terminal object, but the bottom element is not guaranteed by the initial object because the initial object is just the empty object. So already for the bottom, you have a problem. So it may be that you have an if and only if you just remove the bottom object from the complete hygiene algebra. Yeah, but indeed that's a question.
Excellent.
Thank you.
Thanks.